CR radiography is an older form of radiologic imaging than is DR. In many ways, it is like film screen technology, in that individual cassettes are used for each view in an exam. The cassettes need to be marked or linked to patient information and subsequently scanned by a separate device, much like a processor. In this presentation, we will explore how a photosensitive phosphor plate works, how an image is scanned and subsequently transferred to a computer screen. I assume that you know what a pixel is and how to calculate the number of shades of gray a pixel can display. If you're unfamiliar with any of these topics, my channel has presentations covering these concepts. Additionally, my channel contains 2 modules that highlight the inner workings of a DR imaging system. Before we begin discussion of how CR imaging works, let's step back and take a look at a piece of recent radiographic history, specifically the intensifying screen. Below is a representation of an atom in the intensifying screen's active crystal layer. Its job is to convert X-rays into visible light, and that light subsequently exposes the X-ray film. In the right of this illustration is an incoming X-ray photon marked with a P. This photon speeds towards the electrons in the atom. The photon strikes the electron, and the electron is ejected from its shell. Almost instantaneously, the atom then pulls an electron from a higher orbital to fill the hole created by the ejected electron. When the second electron drops, it releases excess energy in the form of a burst of light, and that light exposes the X-ray film. You may be wondering why I'm presenting this nugget of X-ray history. The answer is that PSP plates are similar to intensifying screens in their use and function. PSP plates convert X-rays into light like intensifying screens, but with one important difference. The illustration below represents an atom in a phosphor crystal of a PSP plate. It looks similar to the previous example. The incoming X-ray photon on the right side of the screen. The photon again speeds towards the electron and dislodges it from the shell. But in this case, the electron doesn't leave the atom. The electron jumps to an excited state between the orbitals and is trapped in this position. PSP plate electrons can remain in this excited state for some time until scanned by an infrared laser. When the trapped electron is hit with the energy from the laser, it drops back to its original state, emitting a burst of light. The amount of light a PSP plate produces in each area is proportional to the number of X-rays striking that area of the plate. Let's take a minute to compare intensifying screens to PSP plates. The intensifying screen instantly converts X-rays to light, and that light exposes the X-ray film. The cassette is reloaded for use. The film is then processed and used to display and store the image. The size of the crystals in the phosphor layer affect the speed of the screen and the spatial resolution the screen can project onto the film. While similar to intensifying screens, PSP plates have a significant difference. When X-rays strike the phosphor layer of the PSP plate, their effect is temporarily stored by the plate as a virtual or latent image. The plate is then scanned with an infrared laser, and the light emitted by the plate is proportional to the amount of X-ray energy striking that area of the pixel. The amount of light emitted by the pixel is translated into a binary number, and that number is sent to the computer for display and archival storage. The size of the pixel is ultimately controlled by the laser dot that scans the plate. Many scanners can vary the size of the laser dot using lenses. Here we have an X-ray table, a patient, a PSP plate, and an X-ray tube. The box to the lower left corner of the screen represents the final image displayed on the computer screen. The tube is energized, and the radiation passes through the patient. After scanning, the image is displayed on the computer monitor. The dark areas of the image represent areas exposed to large amounts of radiation and pixels that contained many trapped electrons, whereas the light areas masked by the metal fillings have pixels exposed to small amounts of radiation and subsequently had few crystals with trapped or excited electrons. Let's simulate the process used to read a PSP plate. First, the scanner has a mechanism for extracting the PSP plate from the cassette. Above the plate is an infrared laser that scans the plate. There is a lens that focuses the laser and changes the size of the pixel. A rotating or rocking mirror is used to move the laser across the plate's surface. Finally, there is a light pipe that spans the width of the PSP plate and directs any light produced by the pixel into an electronic light sensor, which measures light intensity as the laser dot moves across the plate. Here we see the scanning process, and the plate is moving under the laser beam. All the time, the light intensity per pixel is converted into a binary number and sent to the computer for processing, display, and storage. The scanning process takes just a few seconds. Once the plate is scanned, it passes under a bright light to completely erase the plate. Then the plate is returned to the cassette for reuse. The illustration below is a summary of the scanning process. The plate moves through the scanner while the laser scans perpendicular to the plate's motion. The laser projects a small dot onto the PSP plate the size of the pixel. So by changing the size of the laser dot, the size of the pixel will change also. It should become as no surprise that smaller cassettes may be scanned at higher resolution than large cassettes. Imaging of small body parts often requires a higher level of detail for proper diagnosis. I've added two arrows to the image that depict the PSP plate's travel direction and the laser scan direction. It is important to know the scan direction of a particular size of cassette. If on grid images you end up with moire artifacts, knowing the scan direction can aid in the diagnosis of the problem. Refer to my presentation on grid frequency for more information regarding moire artifacts. Let's spend some time and see how the pixels on a plate are converted into an image. For this example, we will use a simplified hypothetical PSP plate. To keep things simple, we will limit the plate's dimension to 9 pixels wide by 9 pixels in length. Our plate has a total of 81 pixels. Real PSP plates have literally millions of pixels. Computers are good at sorting and making sense of large quantities of data like this. Furthermore, to keep our example simple, we will only devote 1 bit or memory location to each pixel. Pixels with more than 50% of their crystals producing light will have a 1 assigned to their memory location. Any pixels that don't meet the 50% threshold will have 0 applied to their memory location. Since one memory location is used to store image data, only one memory location is needed to display the image on a screen. Any pixel memory location containing a 1 will be displayed as black, and any pixel memory location containing a 0 will be displayed as white. The grid in the middle of the screen represents our exposed 9 by 9 imaging plate, and the blue box above our computer's memory. Let us prepare the plate for scanning. First, we scan row 1. All the pixels in this row contain no trapped electrons, so all memory locations record 0. Upon scanning row 2, notice the 2 pixels on the left and 2 on the right produce light when scanned, so these pixels are represented by 1s. To save time, we will scan the remainder of the plate. Note how the pixels with the trapped electrons light up when scanned, and how their memory locations are each assigned a 1 as its value. Now we need to move the data into memory. The memory locations are mapped onto a rectangular grid of pixels so that our eye can make sense of the image. The memory locations are copied into screen memory, and the image is reconstructed as a grid of numbers. While you may be able to make out an image at this point, for many, a grid of numbers doesn't look like much. Screen memory doesn't display numbers, it displays shades of gray. In the case of our computer, as pixels that are either black or white. Now, what is visible is a PA skull image. Not much contrast resolution because of the low number of memory locations devoted to each pixel. Before we end this lesson, a word of warning. During normal processing cycle, a PSP plate is erased before it is returned to its cassette. Unlike X-ray film screen systems, PSP plates can be fogged by background radiation. If a plate is stood unused for a period of time, it is a wise precaution to run the plate through an erase cycle before first use in the morning. If you are unsure a plate has not been recently erased, it just takes a few minutes of time to pre-erase it before use. While background fog may not spoil the image to the point of necessitating a retake, fog will diminish image quality, especially contrast resolution. To provide a real-world perspective to this discussion, let's take a look at the specifications for an AGFA CR25 imaging system. The spatial resolution for a CR25 can range from 6 to 22 pixels per millimeter. 10 by 12 plates are scanned at a resolution of 10 pixels per millimeter, and 14 by 17 plates at a rate of 6 pixels per millimeter. This corresponds well to unaided sight. At a normal viewing distance, the eye can resolve about 8 to 12 pixels per millimeter. So a 14 by 17 plate will record about 2,320 pixels across its width and 2,826 pixels along its length, for a grand total of 6,556,320 pixels on the plate. Finally, the plate reserves 12 bits per pixel, which means each pixel can be one of 4,096 shades of gray, between the extremes of black and white. Probably the biggest problem attached to CR technology is the workflow during the examination. If you're migrating from film screen technology, you will find the workflow very similar to CR. To prepare for an exam, collect the cassette needed, one view per cassette, and erase them if necessary. At this point, you may want to mark each cassette with patient information and which view the cassette will hold. Some CR systems may reserve the marking step to prior to scanning, but at some point during the examination, the cassette must be linked to the patient and view information. During the exam, we need to select the cassette for the current view, load the cassette into the bucky tray, position the cassette and the patient, set the technique and make the exposure. To complete the exam, swap a new cassette into the bucky tray and repeat these steps many times as necessary. Post-examination activities involve loading the cassette into the scanner and waiting for the cassette to be scanned, erased, and reloaded. This can take from 20 to 30 seconds. Some scanners will accept multiple cassettes in a processing queue. If you didn't link the cassette and particular patient and exam to the cassette, you will have to do this step before processing the image. At this point, the image is ready for review, evaluation, and to be sent to your PACS system. Probably the biggest attraction of a DR radiography system is the improved workflow feature. A single imaging plate can be used for the entire examination. After each exposure, the plate reads its exposure information, sends that information to the computer, and erases itself within the span of a couple seconds. For instance, a lumbar spine series can be completed without removing the imaging plate from the bucky tray. Just position, center, collimate, set technique, and expose each view. To prepare for the exam, select the patient information from a work list and specify that you are ready to perform the first view. This action automatically links patient information to the current exam and to each view. During the exam, you position the patient, center the imaging plate, collimate, set technique, and expose. The completed image should come up on your computer screen within a few seconds. Go on to the next view. There's no need to swap out the cassette. When you complete the last view, the entire exam is ready for review. There's no waiting for the scanner to read the image. Any repeats or additional views can be completed before the patient leaves the table. Thank you for your attention. This will end the lesson on computed radiography.